Okay, so let's start with the next and last Harvard session. Our speaker today now is Andrew Dzurak from the University of New South Wales. He's the head of the semiconductor non-fabrication facility at the node there of the Australian National Fabrication Facility. He's been working with silicon qubits based on phosphorus dopants since 1998, so he's essentially a world leader in the field. So please, whenever you're ready.
Thanks very much, and thank you very much to Mark and all the organisers for the invitation to be at this meeting. It's a fantastic meeting. I've been enjoying it very much so far, and I'm looking forward to tomorrow as well. Really great, broad range of topics, and it's great to see all of the industry engagement that Bristol have managed to put together here for this meeting. So my talk is going to be about CMOS-based quantum processing using spins in silicon. And I'm kind of echoing a bit here. The motivation for this is to see whether we can take the sort of technologies that we carry around in our mobile phone every day and in our laptop, ubiquitous silicon CMOS processors, and use the same devices to make a quantum computer. This would obviously be a great thing if it can be achieved. I know that probably the majority of people in this audience aren't so familiar perhaps with spin-based quantum computing or silicon-based quantum computing. And so my aim here is not necessarily to make you experts in this area, but at least to perhaps give you an opportunity to decide whether you think that this proposal is viable to actually use CMOS manufacturing to make a quantum computer, and also to look at some of the advantages and disadvantages of a silicon-based approach. The work is, as you heard, I've been working in this field now for approaching 20 years, and so I want to begin not diving straight into the CMOS approach that I'll spend on the majority of my talk, but I'll introduce it from a historical perspective as to how the whole field of spin-based and silicon-based quantum computing evolved, and how we got to the point of looking at CMOS as a viable pathway. So one of the key motivations for exploring silicon-based quantum computing is really summarised by this photograph here. The CEO of Intel from a few years back there, holding up a 12-inch wafer with a couple of hundred Intel microprocessor chips, Pentium microprocessors, and each one of those microprocessors having more than 1 billion CMOS transistors on them. And the manufacturing of these transistors and of this type of technology is really the most advanced manufacturing that's ever been developed on this planet. And so if one can utilise this, trillions of dollars of sunk investment and 6 decades of knowledge of the silicon-MOS system and use it for quantum computing, then this would obviously be a great advantage. But of course, there are many challenges. If it was only for the manufacturing, then silicon perhaps wouldn't be such a prospect. But the other factor is the top part of the right-hand side of this plot, and this is the fact that at cryogenic temperatures, where these type of quantum computers will be operated, the coherence times of spins in silicon were known going right back to the 1950s by the work of Thayer and Gordon and Bowers, to know that the spins could be alive in electron spins for up to seconds and up to minutes for nuclear spins. That in this case, the nuclear spins being the nuclear spins of impurity atoms such as phosphorus in silicon. So the first, in fact, experiments of electron spin resonance and nuclear magnetic resonance in semiconductors were performed on phosphorus in silicon, and these very long coherence times were observed. The reason for this related to the weak spin-orbit coupling in silicon and also the low background of nuclear spins, as I'll show you in a moment. So these two motivations is what led Bruce Kane, who was a research fellow at UNSW in the 1990s, to come up with this really remarkably visionary proposal which I think has, many would agree, drove forward spin-based quantum computing and certainly was the reason that there is now so much interest in silicon-based quantum computing. And Kane's proposal was based around using phosphorus donor atoms in silicon. So for those of you less familiar perhaps with semiconductors, phosphorus, because it's from group 5, has an extra electron compared to its host crystal silicon. And that extra electron in normal silicon is the conduction electrons that give conduction in our integrated circuits. But at low temperature, those electrons will remain bound to the positively charged phosphorus ion. And in this way, Kane proposed the idea at low temperature of localizing electron spins bound to those individual phosphorus atoms. Now, that's kind of the key physical driver, but the technological driver that he wanted in order to make this happen was the ability to position these atoms with near atomic precision or as close to atomic precision as possible and aligned to some control electrodes that are used to manipulate both the electron and the nuclear spins. In Kane's original scheme, the idea was to use the nuclear spin because of these extremely long coherence times. Okay, so that then led to, in Australia, a very significant effort now being explored around the world by other groups to work out how to make such devices with single atoms. And so there are two main approaches that have been taken for this type of technology. One approach using scanning probe lithography. This is the approach taken by the group of Michelle Simmons at UNSW to position individual atoms. And the other approach using a more conventional manufacturing process of ion implantation is to use ion implantation to implant individual phosphorus atoms aligned to control electrodes in order to configure the qubits. And to date, the demonstrations of single atom qubits of phosphorus in silicon have all been demonstrated using this ion implantation route, which has some advantages from the perspective of convenience of device assembly and manufacture. And so I just want to highlight really just the last 6 years of work on those donor qubits. Primarily from the perspective of explaining the approaches that my group is taking with the silicon-CMOS approach. And by the way, I should thank Thaddeus Ladd for his excellent talk earlier. He very nicely went through the different ways of confining electron spins in devices, in particular in silicon. So this first approach of using atoms to confine, and I'll be moving on to the approach of using gate electrodes to confine the silicon in MOSFET transistor-type devices. So this result from 2010 was a crucial breakthrough in terms of realizing single atom qubits and indeed silicon qubits in general. This was the first demonstration of the single shot readout of an individual electron spin bound to one of these implanted phosphorus atoms. And the process is summarized in these cartoons. These two levels are meant to represent the Zeeman split levels in a large DC magnetic field of order a Tesla or so. This dotted green line represents the Fermi energy in some electron reservoir. In this particular experiment, this reservoir was in fact a large collection of electrons in a quantum dot or in a MOSFET-type transistor that was adjacent to the implanted atom. And the process of spin readout is just by spin selectivity, in the sense that if one biases the Fermi energy in the dot in between the Zeeman levels, then a spin down electron does not have the energy to get into this reservoir, but a spin up electron can. And so if we monitor the charge motion with, in fact, in this case, the single electron transistor reservoir acts as its own sensor in order to sense as a very, very sensitive electrometer, then one observes the blip when the electron tunnels into the reservoir, and then a short time later a spin-down electron tunnels out into the spin-down state, and this constitutes a fingerprint of a spin-up state as opposed to this experimental trace. This is raw data taken, you can see, over some hundreds of microseconds in this example of a single-shot readout. And in this experiment, it was shown that the T1 spin lifetime was many seconds, which was known from ensembles, but not yet shown for single atoms. And after having the spin readout, the next step then is to control those spins. So if we have a look at this device here, this structure here, I'll show more about these devices later when we look at our MOSFET qubits, but this constitutes the single electron transistor device, which creates this reservoir. It's configured next to an implanted phosphorus atom or a few phosphorus atoms. So this is the readout part of the device as shown a couple of years earlier, but now the device is configured with an on-chip microwave transmission line, and by applying a gigahertz AC current, one can produce an AC magnetic field, quite broadband. It can go from megahertz to gigahertz, and in this experiment in 2012, it was shown that it was possible to rotate the electron spin and perform Rabi oscillations. Using exactly the same type of device, it's also possible to access the nuclear spin states, and here you see Rabi oscillations of the nuclear spin controlled by, again, this same transmission line, but now pulsing at megahertz, which is the corresponding nuclear magnetic resonance transmission resonances for the nucleus. So in this one device structure, using on-chip electron spin resonance and nuclear magnetic resonance, it's possible to manipulate individual electron spins and individual phosphorus nucleus spins. And these basic techniques of reservoir readout and electron spin resonance, as you'll see in the main part of my talk, is the techniques that we use for controlling the qubits in our CMOS devices. So I already talked about the fact that silicon has these long coherence times, and one of the reasons is because in silicon, it turns out that most of silicon isotopes are silicon-28 and silicon-30 naturally occurring, and around 95% of them, and those isotopes have no nuclear spin. Only 5% of the nuclei are silicon-29 in naturally occurring silicon, and this low background of nuclear spins can perform these flip-flop interactions with each other, causing small fluctuations in the local magnetic field seen by the electron wave function, shown here as this blue cloud around a phosphorus donor. And these, therefore, can cause decoherence of that electron spin. But the good news is that one can improve the coherence times even further by isotopic purification of the silicon using standard nuclear processes for isotopic purification, developed obviously originally in the nuclear industry. And so in ensemble systems, it had been shown that for phosphorus in silicon, it was possible to get electron spin coherence times as long as 1 second in 2011. And in the last couple of years, this paper from late 2014, this was then using one of these same donor qubit devices in isotopically purified silicon-28, and we see here Rabi oscillations of the electron spin going on here for over 100 microseconds, and to compare that with the result from 2012 in natural silicon, you can see those Rabi oscillations dying in about 1 microsecond. So a massive improvement in coherence by using this isotopic purification. In fact, and you'll hear more about this remarkably long coherence system that's available for single atom qubits. So the electrons from Andrea Morello tomorrow will go into this technology in much more detail. But the electron spin here, it's possible with dynamical decoupling to push that out to ½ second, and for the nuclear spin out to a remarkable 30 seconds. So Andrea Morello will talk about how this type of single atom technology can be potentially scaled up to full-scale quantum computing and some of the designs and challenges for that. I'm just going to leave donors here by saying that clearly these donors can have remarkably long coherence times and commensurately very high fidelities, but manufacturing them does remain a challenge. You'll hear from Andrea about a variety of ways to get around some of those challenges, but I now want to move to an approach in silicon using, as I said, more conventional approaches for devices, really just copying what is already available in CMOS technology. And as a segue into the discussion on the CMOS qubits, I want to draw your attention to this convergence of ideas that occurred in the same year, both in 1998, the same year as Bruce Kane conceived of this idea of using the spins of phosphorus atoms in silicon. This paper came out from Daniel Loss and David DiVincenzo, looking at using spins in this case, in gallium arsenide originally. That was what motivated them. Gallium arsenide quantum electronic devices, in particular quantum dots, had just at that time reached the stage of being able to confine single electrons. And they then proposed the idea of taking these single electrons confined in electrostatically gated structures and using the spins to encode quantum information and to do quantum computing. And that paper then motivated significant efforts in the gallium arsenide nanoelectronic device community, for example, from the Marcus group at that time in Harvard, with this experiment from Jason Petter, and from the group in Delft from Calvenhoven and van der Sijpen, this paper by Frank Coppens in 2005 and 2006. In the Harvard result, they took two quantum dots in gallium arsenide and were able to create one of these singlet triplet mode qubits. You heard a little bit about the singlet triplet approach from Thaddeus Ladd earlier today. And in this approach, they actually, although there are two quantum dots here, they're actually just using the electron in one quantum dot, and they controlled that with electron spin resonance, very analogous to the approach I showed you for the donor earlier. So here in 2005 and 6, in gallium arsenide, were the first realizations of single spin manipulation and qubit control, as per the Loss and DiVincenzo paper. And this work continues today with very, very impressive results from groups all around the world working on gallium arsenide spin qubits. But there is one fundamental challenge that faces that approach, and that is that unlike silicon, there are no nuclear-free spin isotopes of either gallium or arsenic. So in other words, the gallium arsenide lattice is fundamentally full of fluctuating nuclear spins, which are going to fight against the coherence of your qubits. And I will note that the gallium arsenide qubit community have developed some remarkable techniques to polarize nuclear spins to try to mitigate against these effects by clever decoupling schemes, but fundamentally one cannot get around the fact that you're sitting inside a fluctuating bath, which is not the case in silicon. And so moving now then to silicon, in this case, the silicon germanium system that Thaddeus also spoke about this morning, I want to cover really a coverage of the state of the art in quantum dot-based approaches using that silicon germanium material system. And as Thaddeus said, one of the motivations for using silicon germanium as a platform is that one can obtain quite, really very good interfaces between silicon and silicon germanium. Not quite as good as in the gallium arsenide AlGaAs system, but nevertheless, one can get quite low disorder interfaces. And so there have been a variety of different device designs and demonstrations of qubits using silicon germanium. So just to cover a few, this really first work, groundbreaking work in silicon germanium from HRL Labs in which they demonstrated a Singlet triplet qubit in a double dot system. This was in naturally occurring silicon. And then this is a paper describing the work that we heard in more detail from Thaddeus, in which they took a triple dot system to encode a single qubit in an exchange-only manipulation, using only gate voltage control to manipulate this qubit. And in this case, it was in isotopically purified silicon, and the dephasing times here in the approaching 10 microseconds or so in these experiments, primarily limited by charge noise fluctuations. And then in another group in Wisconsin, the experimental group led by Mark Erickson, they've also used silicon-germanium quantum dots. In this case, a double quantum dot system, but they encode the information in a combination of spin and charge. Because it has a charge component, the dephasing time is rather rapid at 2 to 10 nanoseconds, but by using very, very fast gate pulsing, which is possible because they're employing the charge degree of freedom, they're able to get, really very high quality Rabi oscillations with fidelities approaching 90% for some of the gate set that they are looking at. Finally, two other approaches in the silicon-germanium system, just to really close off the field of silicon qubits before I move over to our CMOS approach. Here are two different experimental groups. This one from Delft, Lieven van der Sijpen's group in collaboration with Mark Erickson, where they've made, in this case, it's effectively a single quantum dot, depletion gate defined quantum dot, and they've configured a micromagnet on the surface. This micromagnet is used to create a magnetic field DC gradient, and then when one applies an AC electric field to move the electron through this magnetic field gradient, one creates what's called electrically driven spin resonance of the spin, and one can perform spin rotation. And you see here the familiar chevron pattern of a Rabi oscillation here for this single spin qubit. And most recently, just published on the archive a couple of months ago, they've performed randomized benchmarking, and by pushing the operation speed up, they've managed to get a control fidelity of 99% for that qubit. The section below here shows work from Siego Tarucha's group, who were one of the real pioneers of the gallium arsenide quantum dot qubit approach. Now, for the first time, moving to silicon-germanium, motivated by, obviously, the long coherence times available in silicon. And they've used effectively the same approach of micromagnets and been able to push their control gate fidelity up to 99.6%. So very important and significant results. Okay, so I wanted to really use my talk to give an overview of what's going on in the silicon spin community, but now moving completely on to the work with our MOS quantum dots. So the device structure that we have is effectively a MOSFET. So the light blue is silicon, the dark blue is silicon dioxide, and the grey here is an aluminium metal gate. By putting a positive voltage on the gate, we induce electrons. We have here a heavily N-doped source and drain to provide and take out the electrons, so current can pass through here when we turn on this voltage with a positive voltage. This is just a standard MOSFET. The difference here is that we've added 2 extra gates which can locally deplete to create tunnel barriers here and here and isolate a quantum dot. Now this type of silicon-MOS quantum dot is the same readout device that was used to read out those phosphorus donors in the previous papers. And if we change the gate voltage, then we see that we can change the occupancy of the dot. These are so-called Coulomb blockade oscillations in the single electron transistor. You can see they're very high quality as we populate individual electrons into the device. I'd like to emphasize the fact that this device structure, following the same sort of technology as is used in these CMOS devices. The main difference is that in manufacturing, these gates for many years have been polysilicon, although they're now moving towards elemental metals, but the point is that the basic structure is the same of metal oxide semiconductor stack, with the electrons here confined up at that interface in the same way as happens in standard CMOS. And although in our demonstration devices we're working with elemental metal gates of aluminium, there's absolutely no reason this platform can't move to using the same sort of gate structures as are used in industry. This is just a slide showing some of the capabilities at our university, UNSW, our CMOS manufacturing, and also high-resolution electron beam lithography to create our gate electrodes. So now, this work from 3 years ago showed in one of these gated devices. This is, I won't go through this device, maybe just look at the cartoon. We use a gate structure to isolate a puddle of electrons in this quantum dot. These electrons can tunnel to this reservoir in the way I showed in the spin readout on the donor, but now we're confining the electrons in our quantum dot. In this work, we show that we can, this is the charging energy measured of the energy to charge this quantum dot. As we increase the number of electrons, this charging energy goes down because the capacitance increases, and so the charging energy increases as we make the dot smaller. But we see jumps in the charging energy at filling factors of 5 electrons and 13 electrons, and this can be understood by looking at the level filling into this, what is effectively a circular, the circular Fock-Darwin states of this quantum system. In Fock-Darwin states, we have 1 ground state and 2 orbital excited states. With spin degeneracy, this would lead to shell filling at 3 and at 7 electrons. But in silicon, there are 2 valleys in the conduction band that are important in 2 dimensions. So silicon actually has 6 valleys that are degenerate in bulk. When we confine to 2 dimensions at an interface in MOS, we then have 2 nearly degenerate valleys, although these are slightly spin split. So in this experiment, we're not able to resolve the spin splitting between these 2 valleys, but in an experiment that we showed here in this paper, we were able to show that when the Zeeman splitting of the levels in the lower valley reached the valley splitting, and we had a crossing over of the spin and valley states, we had an enhancement in the spin relaxation rate, and this allowed us to very accurately read off the valley splitting in our device. And we're able to show then, from that experimental data, that we could control the valley splitting using just gate voltages on this device. The reason this is very important is because we want our qubit manifold to just be the spin down and spin up states. We don't want them mixing into those other valleys. So this showed that we can push that upper valley away and in silicon and operate just as a pure spin qubit. Just one slide here to show some other work that we've been doing, not qubit related, but using these quantum dots as electron pumps that can operate up in the gigahertz regime. This is currently, so this work was from 2 years ago, where we showed that these pumps could be the most highly accurate pumps in silicon, and at the moment we've got a collaboration with MPL here in the UK where we're currently reaching effectively world record accuracies with the aim of bringing this into defining a new SI unit of current based purely on these pumps. Okay, so the approach then for our CMOS dots is to take natural silicon, add a layer of 1 micron of silicon-28, and then manufacture our device on the surface. The silicon-28 is supplied in a collaboration with Professor Koito from Japan. And in this paper, we showed that when we confine our quantum dot under one of these control electrodes, this red control electrode, if I zoom in through a cross-section, I'm effectively just confining 1 or more electrodes underneath this gate in this MOS structure. This just shows the depopulation of electrons down to the last electron, and this is showing one of these single spin readout events using the same spin to reservoir tunneling that I showed earlier. Up here we show the Rabi oscillations of the electron spin. Again, on this device we have this on-chip microwave line to perform electron spin resonance. You can see the long coherence times. The T2 star, a remarkable 120 microseconds, Hahn echo at 1 millisecond, and with dynamical decoupling out to tens of milliseconds. One of the most important aspects that we found about this qubit was that by varying the electric field on the device with a gate voltage, we could tune the electron spin resonance frequency by many, many times the line width. In silicon-28, the ESR line width is only 2 kilohertz, remarkably narrow, and we can push the ESR frequency by tens of megahertz. This means we can address literally thousands of qubits within this space, or alternatively, we can keep a constant ESR frequency on and switch our qubits into and out of resonance. And in this type of concept, we see a paper from Andrea Morello's team using that same idea, in this case tuning donor qubits in and out of resonance while keeping a constant ESR field. We've also shown that we can operate these qubits not just in the lower valley, but also in the upper valley. If we have 3 electrons, the 2 electrons form a singlet in the lower valley, and then we can manipulate the upper qubit. We've studied the G factor of these spins in both the 1 and 3 electron case, and we find, and I didn't mention this in the last slide, but the control of the ESR frequency is through a small change in the G factor of the electron. As we distort the electron wave function, we change its G factor. This is the way we're able to address electrically our qubits. And it turns out that the electrons in the different valleys actually change their G factors in different ways via a mechanism now understood through modelling from Risko Riskov and Charlie Tahan at Laboratory for Physical Sciences in the US. We've characterised the control fidelities for both the 1 and 3 electron qubit by randomised benchmarking. The 1 electron qubit showing 99.6 fidelity average. All of the gates show fidelities above 99% for the 1 electron qubit. For the 3 electron qubit, those fidelities are a little lower due to the fact that it's more exposed to electrical noise due to a bigger dependence of the G factor on electric field. We've also done some theoretical studies of how low frequency noise in the device can modify the randomized benchmarking analysis. In pure randomized benchmarking theory, assuming Markovian noise, one expects an exponential decay, a pure exponential decay of the composite fidelity of the Cliffords. We find experimentally a non-exponential decay, which can be understood by the fact that we're causing detunings across a large ensemble of measurements for the randomized benchmarking, and when we add a group of exponentials, we arrive at a sum which is not an exponential. And so this leads us to the belief that if we can do dynamic modification of our tuning, we should then be able to get even higher fidelities than 99.6 we've already shown. Finally, I want to show that in this exact same device, we've operated multiple qubits. So if we zoom in, this is this single electron transistor sensor that's used as the electrometer. The electrons tunnel out to this reservoir, and each one of these gates can confine one quantum dot, either one or more electrons. The way this is done is that the aluminium gates have a small layer of aluminium oxide which insulates them from each other and creates a natural tunnel barrier between the dots. So each gate, one gate provides one dot, so a very compact arrangement. And in these devices, we've been able to operate a qubit under each one of those gates. So each one of those quantum dots, each one of those quantum dots has a high fidelity qubit that we can control and tune, each one with a different ESR frequency. And the fact that we have different ESR frequencies in the different dots is important, because if we're going to control a qubit logic gate, we need to address each one of the qubits independently. So in this plot, we're plotting as a function of the gate voltage on controlling dot 1 and the gate voltage controlling dot 2. This is just showing the depopulation of the electrons out of the dot down to in here the 1-1 state. It's just the Rabi oscillations of each of the independent qubits. And this is the showing the energy level diagram of, these are the 1-1 charge states, so these correspond to one electron in each dot for all of the 4 possible spin combinations of the 2-spin system. And here is the 0-2 charge state, which is a singlet state. The triplet state in this case is much higher. And we have an anti-crossing here between the 0-2 singlet state and the up-down and down-up states in the 1-1 manifold. And as we approach the 1,1 to 0,2 charge transition. So as we move closer to this transition, we're able to increase the exchange coupling between the two spins. And in this experiment, we experimentally map out the resonance frequency of qubit 2, and so we can actually map out the Hamiltonian in this experiment directly using our ESR measurement process. You'll notice that the ESR signal is starting to die away as we get close to the anti-crossing. This is because if we have electrical gate noise here, it'll cause our qubit to decohere in a similar process to what we saw from Thaddeus Ladd's analysis of their qubit. And this is then the final experimental slide I want to leave you on. This is how, in this two-dot system, we can perform a C-not gate. So I'll just spend a minute going through the process of analysis and control. This diagram here, I know at the back it's probably a little hard to see, shows the Zeeman levels of dot 1 and dot 2, the Zeeman split levels in a DC magnetic field. Here is the reservoir. And so in this stage of the readout process, we read out the spin of qubit 2. We then apply a gate pulse to lower the levels, bringing qubit 1 into resonance with the reservoir. So that allows us to read qubit 1 sequentially after reading qubit 2. And in the same process, the spin-down electron comes in to reinitialize qubit 1. Finally, we pull the levels down and we deterministically initialize qubit 2 spin down. So after this cycle, we've read out each of the qubits and we've initialized them both at spin down. It's essentially a pre-initialization. Then, to set each qubit to an arbitrary position on the Bloch sphere, we perform single qubit rotations by applying ESR pulses to that ESR line, first to qubit 1 and then to qubit 2. Remember, we can address them independently with different frequencies. So we can set them up how we want. And then we turn on exchange by pulsing closer to this anti-crossing. Okay, and so how do we create a C-not gate? Well, what we do, in this plot, we show here qubit 1 initialized at spin up, and here qubit 1 initialized spin down. We begin with qubit 2, of course, down. We apply a pion 2 pulse to qubit 2 in both cases. And now we turn on exchange. And now the amount that qubit 2 will rotate around the Bloch sphere equator will be determined by the state of qubit 1. It actually rotates twice as fast when qubit 1 is spin down in this particular arrangement. And so and then finally we finish with another pion 2 pulse on qubit 2, and the final state of qubit 2 will now be dependent on the state of qubit 1. And so if we stop it at this particular time of exchange gate, then we realize a C-not gate, so we flip qubit 2 if and only if qubit 1 is down in this case, and here we measure the anti-correlation between the two spins expected for the C-not gate. So what about scaling? I'll just spend one more minute now, if you'll forgive me, to talk about the prospects for scaling this technology. So many of you are probably familiar with this very nice paper from the Martinez group with Austin Fowler, looking at an approach for a surface code approach for superconducting qubits. Well, what we'd like to do with our CMOS devices is ultimately have a similar close-packed array, although in this case it will be much more close-packed due to the requirement to obtain exchange coupling. Those qubits need to be within some tens of nanometers of each other, but of course this is the feature size of available CMOS today. So we have individual qubit dots, and we also have extra electrodes used for readout and also for control. And just to touch on readout, we heard a little bit from Dave Wecker yesterday about the work of David Riley at the University of Sydney. Professor Riley's been developing an approach called gate-based dispersive readout. This is a gallium arsenide double quantum dot. And what he showed was that just by monitoring, putting one gate into a tank circuit and measuring the reflected microwave power, it's possible to sense the charge state of a double dot system. And ultimately, this can be used for spin readout in our devices as well. So the idea is just with a single gate electrode, we can do spin readout on a pair of spin-bearing dots. And with this sort of approach, what we are therefore aiming to do is to create a highly dense 2D array with control electronics, classical control electronics coupled in an integrated monolithic chip. And my final slide, just to show you where ultimately the vision for this technology is to have a lower layer of silicon-28. Each one of these structures represents an individual quantum dot. And then above here, we have classical circuitry, effectively classical MOSFET transistors, the three-dimensional MOSFET transistors, done in a three-dimensional manufacturing process, which is a process already developed by industry to deal with stacked systems, which also incorporates components of DRAM in order to store on-chip voltages, in order to cope with the inevitable threshold offsets that we're going to get in these devices. And with that, I will thank all of my many collaborators, and I don't have time to go through them, but also our funding agencies, the Australian Research Council, US Army Research Office, and our Australian National Fabrication Facility. And if there are any PhD students in the audience who are interested, we are hiring, and it's a great place to live. Thank you very much.
Thank you very much. And we have time for 2 quick questions. Yes, Mark?
Really fantastic work, very, very impressive. I just want to ask you about your last slide.
Yep.
I just wanted, it's a really quick question. I just want to get, what's the scale on there? What sort of dimensions are we looking at?
I'm deliberately leaving a few details off on this at the moment because it's some work in preparation, but to give you an idea. So this can work with around about 20 to 30 nanometer pitch on that dot. That's effectively what we're currently working with. But ultimately, we'd like to think that we could push this down to the point where these are even, 7 to 12 nanometer type node of CMOS. A key factor here is, which I didn't mention, is that we believe there's no impediment to operate these devices even at the 1 to 2 to 3 Kelvin operating temperature. Okay, because we're not using reservoir readout here, we're using dispersive readout, and then that actually can improve the prospects for readout fidelity in this approach. And the coherence times are still very long at that temperature.
Would you not want to be pushing them further apart, though, so you've got more room to get all the classical control in there and the readout?
So we've done a detailed layout of all of these structures up here, and what we're relying a lot on is three-dimensional manufacturing. But the actual footprint that we'll end up with down below is flexible. So indeed, we can make the lower region larger, but we've got to, as you say, pack in quite a lot above. So there are a variety of different parameters that we can vary around.
Thank you.
Could you please make also comments about the difference between CMOS devices and silicon germanium devices? I mean, in principle, they look similar. I mean,
So I think that what I would say is the following, and I'm choosing my words very carefully because I've got colleagues in the audience who work in silicon germanium. I think that the advantage of silicon germanium is that it's a lower disorder interface than the silicon dioxide interface. That is without any doubt. So that's the advantage largely of silicon germanium. Some of the disadvantages, it's possibly a little bit more difficult to get isotopically purified germanium, but that's not a major impediment. That's ultimately a commercial issue. I would say that one of the issues is that if you're using silicon germanium, then you do have some limitations on the temperatures at which you can manufacture certain process steps. You're diverting a little bit away from conventional CMOS. Not a huge way, but you're talking about epitaxial interfaces and relatively complex epitaxial structures in order to generate strain relief and so on. So that would be my broad brush strokes answer, but I in no way suggest that many aspects of this couldn't be done in silicon germanium as well.
I don't think we have time for more questions, so let's proceed for the panel. Let's thank again Andrew Dzurak.